welcome grade 12. So we're almost on our last legs, and today what we're going to be doing is we're going to be looking at electricity and magnetism. Okay, so the first question we're going to look at is to do with electrostatics. That's grade 11 work. Then we've got a couple of really nice circuits, and I get very excited. I love circuits. Anyway, so let's look at our first question. So here we have a first question, and it says to us, define electric field at a point in words. Okay, so no equation there. And the second one is to draw the electric field pattern for two identical positively charged spheres placed close together in close to each other. Okay, so they're not touching, they're just close together. So remember, we're doing lots of questions and answers, so I'm going to give you some time to do this. Definition is quite easy, but I want to make sure you write it out nicely. So I'm going to give you 2 minutes, and your 2 minutes starts now. Okay, so grade 12s, let's see how you did. Okay, so now I have some space here. Now remember, and this one is a very specific definition, and because it is the definition for the electric field at a point, you have to mention that word somewhere along the way, okay? You can't just go, it's a region of space, because it's not. So what they want, electric field at a point is the electrostatic force. Okay, and we've got to use electrostatic. So it's the electrostatic force experienced, okay, because it's something you're going to experience, by a point positive charge, or positive point charge, or you don't really need to have positive there. But the reason why we probably need to put it in there is because remember, the direction of an electric field is defined by the direction in which a point charge will move, a positive charge will go. So we need to just probably put it in there, placed at that point. Nice and simple. It's not the general definition of an electric field, but it's for specifically, okay? Guys, please, 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 please learn your definitions. They're the easiest marks in your paper. Now, it says to us, draw the electric field pattern for two identical positively charged spheres placed close to each other. And I've already got the two charges. Yay, makes it easier because I can't draw a circle. Not a nice one anyway. So, what we remember here is, first of all, your field lines can't cross. Your field lines are perpendicular to the surface. And of course, with positive charges, they can't meld into each other, okay? So first of all, let's start with the fact that we know we're going to have charges that are going to do that, okay? The field's going to go away. Now, what's going to happen here is normally we would have another horizontal line that would go between them, but we can't because they're not going to touch. So now the field lines do that. And it's almost like we're going to draw a spider, okay? So now the next part is really important because we have two identical charges. That means the number of lines that are drawn on the right-hand one must be the same number of lines that are drawn on the left-hand one. So now they do that. Okay, and then we did another one there, 3 and 4, and that one, and it's like a big hairy spider. Okay, or eyes with some serious eyelashes. Okay, and then we remember that we put the arrows in. And then you're going to probably be sitting there going, but why would this be worth 3 marks? Well, it's worth 3 marks, guys, because there's a mark for getting the correct shape. There's a mark for making sure that all your lines touch your circle for your charge. There's marks, and there's a mark for making sure that none of them cross. So, there might be some marks that are added together here, okay, and then of course for your direction. And often what happens if there's one thing wrong, then you can only get 2 out of 3, even though they might be looking for 3 to 5 things on your diagram. So just be careful. This to me is also easy marks, and this is one of those things that you're probably going to get because it's a nice level 1 question. Now, we get to a question which I think is absolutely marvelous, and yes, you should be worried. Okay, it's really not so bad. It's a maths issue more than anything else. So I'm more concerned that you're getting the science behind this, okay? So they tell us that we have, now in the question it says millicoulombs there. This should actually be microcoulombs, okay? We have a minus 30 microcoulomb point charge, Q1, is placed a distance of 0.15 meters as shown from a +4, so that should be microcoulomb, that was me, that type funny, point charge, Q2 in space, as shown in the diagram below. So we've got the diagram. The net electric field at P on the same line as the 2 charges is 0. So my net field here is 0. Calculate X, the distance of point P from charge Q1. Okay. Big hint. This. Okay. Now, some of you may have been taught to do questions like this in one step. I'm going to say to you that's going to be a problem for this question. And you need to break it up for me. Okay. I need you to consider the field because of Q2, and I need you to consider the field because of Q1 and how they're related to each other. That's the hint for this question, okay? So I'm going to give you 3 minutes. You probably won't get to the final answer, and that's fine. I just want to make sure you're well on your way. So I'm going to give you 3 minutes, okay? And let's see how far you get. So your 3 minutes starts now. Okay, grade 12s, deep breaths. Okay, so how did we do? Are we all like, oh, I don't like this, Josie? This is a nightmare from a maths point of view, okay? But from a science point of view, actually it's not so bad. So I said to you before I gave you a chance to do it on your own that you needed to separate out what happens. So what we're going to do is let's go, well, what is the electric field at P because of Q1? So I'm going to go electric field because of Q1 at point P, okay? So that means I'm going to do K Q1 over R squared, okay? And when I put that in, this is as much as I can get, as I can put in 9 times 10 to the 9, that's Coulomb's constant, okay? Q was 30 microcoulombs, so that's 30 times 10 to the minus 6, because it's micro, and we don't know X. We don't know R, it's X squared. Okay, we're fine so far. Now we're going to do the same thing for Q2, okay? So now we go, well, what's the field because of Q2? So this time, I'm using this equation. I'm not going anywhere near the equation that says E equals F over Q, because I don't know F, okay? This is 9 times 10 to the 9. It was 45 microcoulombs. So that's minus 6. Now comes the trick. Because the distance is actually going to be 0.15 plus the x all squared. Hopefully some of you got to this point and went, okay, so now what? Well, they said to me that E net was 0. Here direction is really important. Q is negative, Q1 is negative. That means the direction of this field is towards Q, it's to the right. The direction for Q2 is to the left because it's positive. Okay, that's important because now, watch what happens here. My E net would be equal to EQ1 plus EQ2P, okay? One of these has to be negative, and it doesn't matter which one you make negative, okay, because together they must give me 0. So if one wasn't negative, there would be a serious problem with this question because you wouldn't actually be able to calculate it, okay, because you wouldn't get 0 when you added them together. So what I'm going to do is I'm going to make to the left negative, so that means I then put this in here. So this is my Q1. Okay, I'm going to minus this whole part. And I'm going to write a little bit small so that I can get it in here. 0.15 plus x squared. And that's all equal to 0. Grade 12s? You have got all the science marks, okay? The science is done. Now it's a maths problem, okay? And because of time, we could spend a lot of time on it, and there's lots of ways to solve this. But if you get to something like this in your final exam and you're like, really? Now what? Please leave it. Your teachers will kill me now. But it's not worth spending another 30 minutes trying to solve this and getting yourself completely worked up because you can't get to X, and then the rest of your exam's a nightmare. Because now this is worth 5 marks. I'm going to tell you now where those 5 marks are for. Your 5 marks are for 1 mark is for getting that equation for E cubed, okay? There's 1 mark for that substitution, 1 mark for that substitution, and then there's going to be a mark for writing this down in some format to get to there. That's 4 out of your 5 marks. From here, it's a maths problem. Now, I'm gonna start you off on the maths. We could be here till Christmas, so I'm not going to do all of it, but I want you to see something which might make it a bit easier, and then I'm going to give you the final answer. Actually, I need to start that a little bit further over. Okay, so if we put this here, okay, and that's x squared, that's going to be equal to this. Okay. And here's a little bit of trick. First of all, those cancel, great. Second thing that you can do, okay, is you can square root these straight away. That will make your life so much easier because that gets rid of the squares at the bottom, okay? But for time, I'm not going to do it, but you need to be able to do that. So when you do this on your own, I need you to be able to finish this so you can go home and practice. You need to get a final answer, okay, of, let's make it so you can see. No, didn't change. Look at that. Okay, blue. There we go. Final answer of 6,68 times 10 to the minus 1, or it's just going to give you 0,67 meters. Okay? I'm going to leave it up to you to do the maths. We've done the science. The science was not so bad. It's just the maths that's a bit of a nightmare. Okay, so now that your brain's sore, take a bit of a break, and then when we come back, we're going to tackle some electricity. I'll see you in a second. Okay, so grade 12s, let's hit a circuit problem. I chose this one specifically because it has to do with power, and we don't deal with power in the grade 12 curriculum. It's grade 11 curriculum that you would have dealt with power before, okay? So I've done it deliberately because I think it's important that you see it. So now it says to us that in the diagram below, we have 3 light bulbs, A, B, and C, which are connected in parallel to a 12-volt source of negligible internal resistance. Yay, no internal resistance. We like that. The bulbs are rated 4 watts, 6 watts, and 10 watts respectively, and they are all at their maximum brightness. Great. Then we look at the questions. Ooh, and now there's only 3 questions to this, but it says to us, calculate the resistance. How will the equivalent resistance of the circuit change if one of them burns out? And how will the power dissipated by the 10-watt bulb change if the 6-watt bulb burns out only? So, I tell you what, let's do this one question at a time. I'm not going to make you do all of these. So here we go. That's the first question. Okay. And hopefully this won't take you too long. So I'm going to give you a minute. Yes, I'm being mean. So I'm going to give you 1 minute, and your time starts now. So grade 12s, are we done? How many of you went, I don't even know where to start? because it's power and there's no resistance and it's all right. Deep breaths. So remember, when we get circuits like this, the best thing to do, okay, and I did this deliberately, it was a bit mean, but I did it deliberately, is we go, well, the current comes out here, gets to that point, and now it can split. So some of the current goes through there, some of it goes through here, and I'm using different colors. That's probably, just go with it, okay? I'm using different colors deliberately, and some of it goes through here, and in fact, it's going to catch up to the pink over there. Let's just do it over here because it does this. Let's just go with it. And then it all comes back together over here. Now, the only reason why I'm doing this with my pretty colors is I want you to see that the light bulbs are in parallel. This first question expects you to remember that in parallel, the voltage remains constant. So each of these light bulbs has the same potential difference, but the current divides, okay? Now, why is knowing that the potential difference is the same important? Because of this 12 volts. This parallel section, these three light bulbs, are the only things in the circuit. That means that all the potential from the cell must go into the light bulbs. So that tells me that this light bulb has a potential of 12 volts. So if we go to this question, we go, well, I want resistance. Great. I know V, it's 12, and I know power, it's 4. Now, on your information sheet, there are 3 equations for power, okay? Power equals V times I, which is also equal to I squared R, which is also equal to V squared over R. So we look at the 3 equations, and we go, I don't have I, so I can't use those, but I do have V and I do have R. So power equals V squared over R. So that's 4. V squared is 12. I want R. Okay? So R is going to be 12 squared, which is 144, divided by 4. 36 ohms. So it really wasn't so bad. We just had to think about it. Okay, so next question. Same question. How will the equivalent resistance of the circuit change if the 6-watt bulb burns out? Write down only increase, decrease, or remains the same. No change. Okay, I don't want you to guess. So I'm giving you a minute, and your minute starts now. Okay, grade 12s, I asked you before I gave you time not to guess. This is so important. Questions like this are going to come up. Now it said, how will the equivalent resistance of the circuit change if the 6-watt bulb burns out? So in other words, I take that resistor out. Here, it's going right back even to grade 8 and 9 work, okay? But this is grade 10 without a doubt. Remember, we add resistors in series to increase resistance, and we add resistors in parallel to decrease the total resistance, all right? So if I take a resistor out of parallel, my total resistance increases. Very, very important. I took a resistor out of parallel, so my total resistance increases. Okay? There's no exception around this. Now, they could ask you to explain it, okay? And the whole point here is that we would know that because resistors added in series, increase resistance, resistors added in parallel, decrease resistance, okay? Very, 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 very important concept. Now, last question. No, last question's part of this one. There we go. How will the power dissipated, in other words, given off by the 10-watt bulb change if the 6-watt bulb burns out? Then they say write down only increases, decreases, or no change. And then you have to give a reason for your answer. So here you can't just guess, okay, because we all like to do that, but now you can't guess. So I want a nice answer. So I'm going to give you a little bit more time than I would normally for these because I need you to be able to write it out properly for me, okay? So I'm going to give you, and it sounds like a lot for 2 marks, but it's not really because I want you to think it through. I'm going to give you 3 minutes to say what happens to the power of the 10-watt bulb, and your 3 minutes starts now. Okay, so I think there's been one of 2 responses to this question. Either it was like, I don't know, I'm just going to leave it. Or, okay, I've got this. And that's what we want. Okay, I've got this. So this is such an important question because how will the power dissipated by the 10-watt bulb change? Guys, what's really important for you to realize here is that the power of the light bulb is actually a constant. Even though the resistance in the circuit changes, your current will change. But remember, if we're using this equation, power equals V squared over R, did the resistance of the 10-watt light bulb change? No. Does the potential difference across the 10-watt light bulb change? No, it's still the only thing in the circuit. That means that the power of the light bulb is constant. So how do we write this down? Because that's important. So we've realized that there's no change. So we answer it with the way they said, no change. Okay, now what do we say? Potential difference and resistance of the light bulb is constant. Okay? Since P equals V squared over R, power remains constant too. And I'm writing this very big, remains constant. Okay, guys, I need to see which equation we're looking at, because remember there were three equations. So here we're going, well, since P equals V squared over R and V is constant, R is constant, P must be constant. Okay, not so bad. These questions are ones where you need to think through it. Think about what happens to the circuit, how it gets affected, all of that sort of stuff, grade 12s. Okay, please don't neglect power from grade 11 because you haven't seen it for a while. That also reminds me, in this section, grade 11 work, make sure you go and look at how to pay for your electricity, okay, cost calculations, because I haven't done an example with that, but it can definitely come up, okay? I think it's time for a little bit of a break, and then we're going to tackle just the most nicest, wonderful circuit. It's a really nice question. It's an unusual circuit, and I think, well, I'm going to love it. I'm hoping you will too. Okay, so we'll see you in a couple of minutes. Okay, grade 12s. Now we tackle the section that either you love or you don't love, and I love circuits. The reason why I like circuits is because they follow the rules all the time, okay? And it's just about thinking clearly. So, what we have here is a battery of an unknown EMF. Not always great, but let's just go with it. So we have an EMF, we don't know what it is, an internal resistance of 0.5 ohms, okay, connected to 3 resistors, a high resistance voltmeter, an ammeter, and the reading on the ammeter is 0.2 amps. So I'm going to write that into the circuit. Okay. Don't worry about them saying that the voltmeter has a high resistance and the ammeter has a low resistance. That really doesn't matter. That's just to tell you that they don't affect your readings, okay? They don't affect the resistance and the current in the circuit. So there's 3 questions we need to go through. Now, I'm not going to make you do all 3 at once, because if you pretty much get the first one wrong, you can't do the others, okay? So we're going to do it step by step. So let's look at the first one. So there's the question again. Okay, so here let's have the circuit over there because it's important. So we don't know what the EMF is. I know that's 0.2. And your first question is to calculate the reading on the voltmeter. Okay, I am giving you 2 minutes and your time starts now. Okay, so how many of you looked at this and went, I don't even know where to start. There's a battery in the middle of the resistors. That's what makes this such a nice circuit, because if we say, well, here comes my current. Current leaves the battery. What happens at this point? It can split up. So some of it goes here, it goes through the two, and you would use highlighters, but we're not going to do that because then we can't see anything afterwards. So we're going to, and some of it, I'm pretty sure you can't see the difference between the purple and the blue. So let's just change this to the pink. So here we go, and it goes through here, and we get to there, and look, it all comes back together. And you know what? This is just a normal parallel circuit. That's all it is, okay? The 2 ohm resistor is in parallel with the 4 and the 8, okay? Now I just want to take this off so I can see those numbers. So when they ask me for the voltmeter reading, whether I find the voltage over the 2 ohm or the 4 and the 8 makes no difference, okay? Now, first prize is to try use the 2 ohm, but I don't know how much current goes through the 2 ohm. However, I do know how much current goes through the 4 and the 8. So if I'm going to use the 4 and 8, I actually have to pretend that I've put the voltmeter over there over both. Okay, so I'm going to have to add them in series. So remember, R equals V over I. Okay, they're in series, so I can add them together. I want V. I is 0,2. So V becomes 0,2 times 12, and then we take out our calculators, and we get 0. No, I'm lying. We get 2,4. You see, this is why you take out your calculators. I actually have done this, so that's why I'm not using the calculator. I'm trying to save some time. 2,4 volts, okay? Good. So, next question. Now, what I'm going to do here is I'm going to write in the information I know. So this is 0,2 amps. I've just worked this out to be 2,4. All right, now you need to calculate the total current supplied by the battery. Okay, I want I total. I'm giving you 2 minutes, and your time starts now. Grade 12s. With a question like this, there's always more than one way to answer it, okay? So please, if you've got your answer another way around, don't worry about it. I'm just trying to show you the simplest way. Okay, now we know that the current that goes through the 4 and the 8 is 0.2 amps. If I can find the current that goes through the 2 ohm resistor, I can just simply add the two together. That's why they asked you to calculate the total the voltage, the V, okay? So I'm going to go back to my R equals V over I equation. So now I'm going to look at the resistance of the 2 ohm, V. I'm going to take the current through the 2 ohm, okay? So that's 2. My voltage was 2,4. I want current, okay? So that means my current is going to be 2,4 divided by 2, which gives me 1,2. However, let's look here. So that's 1,2 amps, but they want a total, so we need to add them together. So now we need to put another statement that says my I total is going to be the current through that bottom resistance plus the 2 ohm. They told me the current through the bottom was 0,2. This is 1,2, so we get 1,4 amps. The other way you could have done this was to use ratios, okay? I am hesitant to encourage you to use ratios just because we struggle to understand what you've written. So often there's just numbers and ratio marks, and as a marker, you look at it and you're like, And remember, your markers can't interpret what you write. So I'm not allowed to, when I'm marking, I'm not allowed to look and go, they meant this. This is what they're trying to say. This is what they were trying to show me, and then give you the mark. You either showed it or you didn't. Okay, so this way to me is far better because it's less likely to be unclear as to what you're going to do. Okay, so last question on this before we get to the last part of this. There we go. So now I know that I total is 1,4. I know that that's 2,4 volts. Okay, and this was 0,2. Now, look at this. They want you to calculate the EMF of the battery. Okay? It's worth 5 marks. That means it can't be as simple as just one equation, all right? It's worth 5 marks. And I'm going to give you 2 minutes, and your time starts now. Okay, grade 12s, I'm pretty sure some of you are going, no way, Tracy, there's no ways this can be 5 marks. Surely the answer is just 2,4 volts, because in the last question you did with us, you said to us if the parallel was the only thing in parallel, then the voltmeter reading is the EMF of the cell. Well, in the first in question 2 that we did earlier today, there was no internal resistance. As soon as there's internal resistance, that's the eraser, that's not going to help us. As soon as there's internal resistance, things change. Okay? That means I have to consider internal voltage. Okay? This reading is your external voltage. So, watch here. This is what we need to get to. EMF is I, R, plus R. R total is the resistance in parallel. Okay, so that means I've got to go 1 over R1 plus 1 over R2, which means I've got 1 over 12 plus 1 over 2. That gives me 7 over 12. You're going to have to believe me, I'm running out of time, so I want to make sure we get all the maths in. Ooh, I'm just doing all weird and wonderful things right now. There we go. Sorry. So, he doesn't like me today. Let's move. There we go. Okay. Extend. Remember, that's 7 over 12. We flip it over, gives me 12 over 7, which is 1,71 ohms. Okay. So, over here, I don't know EMF. That's what I'm looking for. We know I. We just worked it out. 1,4. We know R now is 1,71. They told me the internal resistance was 0,5. We plug all of that into our calculator, 3,09 volts. Be careful with internal resistance, grade 12s. Be very, very careful, okay, because that's where you're going to make mistakes. Grade 12s, the best thing to do with circuits, practice. The more you see, the better you get at it. Okay, so practice, practice, practice. I have run out of time again. These lessons are never long enough, and I will see you next time.